Example 6. Applying hyperbolas to the real world. In navigation, we have what's called a LORAN, which is a long-range navigation. It's a navigational system for ships relying on radio pulses that is not dependent on visibility conditions. Suppose the LORAN stations E and F are located 350 miles apart along a straight shore with station E, due west of station F. When a ship approaches the shore, it receives the radio pulses from the station and is able to determine that it is 80 miles farther from station F than it is from station E. Find the equation for the hyperbola in which the ship is located. And I included here that the difference is always equal to 2a. That's kind of the difference in the two. So let's go over to the next slide here, and let's try to draw a little picture. We know that they're along a shore, and it says E is 350 miles due west of F. So E is over here, F is over here. They're 350 miles apart. And there is some ship located somewhere out here. I'm just going to put it randomly here. And it knows that F is 85 or 80 miles farther than E from the ship. So the reason I put ship towards E is because this distance, whatever this is going to be 80 less than this one. Said another way, if this is X, this is going to be X plus 80, if that makes sense. Now to help us solve this, here's what I'm going to do first. Is I'm going to put this, and I'm just going to make the center be right there. And if I do that, then that means E is going to be located at left 175, 0, because these are 350 apart, and F is going to be at 175, 0. We still don't know the ship's location, but we're trying to write an equation. Now, for these to work, these stations are set up at the foci. They're always like the point that sends signals or receives signals. It's always the foci, which means our hyperbolas are going to come around it this manner. And it's going to be when they cross, but it'll be like this and like this on the other side. So these are our hyperbolas that we're going to be working with. So if we wanted to start with an equation, we know it's horizontal. So I'm going to have my x first over some value, and it's going to be minus some value for y squared, and all of this will equal 1. Now this tells us the difference is 2a. So this 80 here is our 2a. So 2a equals 80. So a equals 40. And so it'll be 40 squared when it goes right here. And when I square, whoops, I'm sorry, I didn't mean to square it right there yet. I meant to write a squared would equal, well, 40 times 40 would be 16 with 2 zeros. So that's what will end up going right here. Not only that, we know the center is located here. So I'm going to replace the top, since our center is at the origin, with just x squared, and here with y squared. Now, let's look back at our problem. What else can we determine? Well, we know that the foci are 175 and negative 175. That means my C is plus or minus 175. Since that's the case, C squared we could find by squaring those values. So I'll go to the calculator, 175 squared, press enter, I get that large number, 30625. 30625. To find my b squared, I'm going to use the formula. C squared equals a squared minus b squared. C squared is 30625. That'll equal my 1600 for my a squared minus b squared. I'll subtract over the 1600. And I believe I get 20. No, I'm off a line, I'm sorry. Or it would be 29, 20, let me make sure I just don't mess this up. Minus 1600. 29025. Okay. 29025 equals negative b squared. So we could say that b squared equals negative 29025. Well, since the negative is already there, we just put the 29025 there. This is my equation. Now I'm going to go to part B. It says find the exact coordinates of the ship if it's 125 miles from the shore. Now I'm going to pause this and copy over some information from part A. Okay, now I have it copied. And so if our hyperbolas are working this way, and I don't know if I ever explained this, this signal might be sent out and it would hit the ship here. And the way it knows that this one's longer is because this hyperbola, as this signal extends out from F, would hit it over here. And we'd say a hyperbola, it would actually look like coming out. F is sending out, it would be sending out like pulses. It would go boom, and then another pulse would go out, and then another pulse would go out. And so it would hit it, and we just kind of cut off the shape to make it look like a hyperbola. This one would be doing the same thing, just sending pulses out. And it would hit this pulse from E before the pulse from F. So that's the kind of an explanation of how this is working. Now the ship is 125 miles from the shore, which means, let me plot this real quick, and I'll do this one in a deep red, that this distance here is 125 miles. Well, that's a y value. So we could plug that into y and solve. So we would have x squared over 1600 minus 125 squared over 29025 equals 1. If we could in-solve this real quickly to find what x is. So I'm going to come over here and do menu 3-1. And the equation is x squared over 1600 minus another fraction of 125 squared. Oops, 125 squared over 29025. All that needs to equal 1, and we'll do comma x. Here is my ship's value. I'm getting, and this will be plus or minus. The way I have it drawn, though, it'd be to the left. So 49.6 is what we're getting for x. X equals 49 point, it should be plus or minus 49.6. Since we're saying it's to the left, I would list the point as negative 49.6 comma 125. Now I have one for you to try. Try this one.